going to present a paper, or I'm going to present a new geophysical system, transient. A transient EM system. The title here is a next generation synthesized EM system for groundwater exploration. My outline here for this talk is I want to talk a little bit about the background, why we are doing this research and why we want to build these kind of instruments. Then I will present you the system, and I will also explain to you how it has been verified. And then I will show some data examples. I have one example from Denmark, I have one example from Kenya in Africa, and then I have a summary. And I'm sorry I don't have an Indian example or an example from India, but that will come. But before I get into the actually details here, there are maybe not so many people using the transient EM method, so that we just dwell a little bit about how the physics of this method works. So basically, one put out a loop on the ground, that is the red coil sitting in the picture to the right, and one also put the yellow coil out, that is the receiver. And then you put out the transmitter put out a steady current in the transmitter coil. Could be 10 ampere, could be 30 ampere. For an airborne EM system, it would be 250 amperes. But basically, set up a static magnetic field, that set up a static magnetic field. And then we turn off that current in the transmitter coil. And when we turn off such a current, then. Oh wait, it's working over here. Sorry, it's on my screen, it doesn't work. I better look over here. When we turn off a current in a coil, we get induction of currents in the surroundings, and we get by that induction of currents in the subsurface. But they also diffuse downwards and outwards and get converted into heat. So they have, of course, also a magnetic field. We call that the secondary magnetic field. And basically, that is the field we measure in our receiver as a voltage. This voltage we measure in our receiver is dependent on the conductivity of the geological layers below us. And then we can, with mathematical operations, inversion, we can back out what is the conductivity structure of the subsurface. So we get conductivity structure the same way as we know from ERT. If you do VES or ERT measurements, it's also resistivity, the resistivity we get of the geological layers. And this is the same from the TEM. So what we want to do here, and this is also the vision of my research at the university and also my research in the company, that we want to build instruments where non-expertly, standardly can get subsurface images from complicated but very simple instruments with integral processing solutions. So we want to make these instruments easy to use. And I'm here emphasizing the word non-experts. It has to be that technicians without a PhD or a professor in geophysics can use these instruments. They should also be able to use these instruments because they are complicated, but we will hide all that complications into the instrument. And then we'll integrate the data processing into the instrument. To get there, we need small and reliable hardware boards, and we need a lot of compute power already in the instrument. We need to integrate IoT, internet, so we can control everything from tablets, and we can also upload data as they are measured. Then we also want to use AI in the processing software, and we want to reduce costs, so you don't have to buy a Tesla whenever you buy a geophysical instrument. And then, of course, we need to demonstrate to the customers and society what they gain from the technology. So this is the idea we're working from. The Esben is the first of our new systems, which is coming from several years of research. It's a brand new hardware platform. It's basically a two-moment system with 1 ampere low moment, 5 ampere or 10 ampere high moment. I'm going to come back to what all that means afterwards. It's controlled by an app working on Android or iOS. The depth of investigation is these 250 to 300 meters at the maximum. The total weight is 23 kilos. distributed with 3 components, and then it has Wi-Fi and internet and all that. This is the instrument box, and you can see here we basically have the control app. The instrument box, the only thing, on the box is basically an on-off button, and then you control everything from this app. Here we are getting the data curves. It has also recording of the position, and you can get a map showing basically where are our measurement stations. One can also upload a map before, so the field crew, has an indication of where we want to go. So simple operation. I want to compare this instrument to the commonly known and used VES. So the VES is a method which is used many places in the world and also in India. So I'm basically showing the simple loop with a 40 by 40 meter transmitter here. And in this system, it takes about 10 minutes to set up and measure. It takes, you can make 15 to 20 stations in a day for 2 persons, and the investigation depth is these 250 to 300 meters. If you compare that to a VES sounding, I think it takes half a day to set up and measure. One get 1 to 2 stations per day, 200 meters, and 1 station if you want to go down to 300 meters, because that requires very long spread. You are at least 5 people in the field, so the production here from these TM soundings is much higher compared to what is known from VES, and also the depth of investigation. I don't have a picture here, but we also make a small loop offset configuration. Basically, these loops are 3 by 3 meters, and then the idea is, and there is a sketch of how that system looks, that you basically have 2 people, one on the transmit coil and one on the receive coil, and they basically carry the system, maybe walk 20 meters, make a measurement for 1 meter, or for 1 minute, carry the system for 20 meters, make a measurement for 1 minute. So one basically get a profiling section of the subsurface, and here you get a depth of investigation of 100 to 150 meters with a system like this. Depth of investigation is always some questions we get. So we have made a modeling of where we calculate the depth of the investigations, and there are some papers on that, and I'm just going to base my calculations here on those measures. So if we assume we have a 40 by 40 meter configuration, standard transmitter loop, and we have conservative noise level, then I'm here showing basically the half-space model. There's a model which is 5 meter, 10 meter, 20, 30, 50, 100, 200, 300, 500, and 1,000 meter half-space. And the depth is showing to the left side 0 to 350 meters, and then the gray line is the calculation of the depth of investigation. And what you can see here, that when we are in these 50 to 500 meter settings, the depth of investigation is 250 to 300 meters. There is a paper, and there are on how this depth of investigation is calculated, and come and ask me if you want to know more details about it. Validation of a system like this is extremely important, and we are validating all our instruments on a site. It's outside, not too long from our office. We have used the same site for more than 20 years now, and it is used for validation of several instruments. SkyTem, the airborne system, is validated on this system, and so is our systems also. And I'm basically here showing the new Esben instruments measured in 2023, and we are comparing that to a reference data set made with the Walkton instrument in 2010, so it's 13 years old data set, and we are using again standard configuration. What we call the test site is that where we have the red square, and then there's been made 11 stations along the dots, reproducing the walk temps from 2010. And basically, this is the result of the Esben. You see, we have a resistor at the top. We have a resistive, relatively conductive layer at the top. Then a resistor, that's the red. Then we have a green color, which is a till. And then we get into a relatively thick very clay-rich still, and then we actually in minus 80 meters has, that's the red color, we have limestone. If I compare this to my 2010 data, we can see we get about the same model, and if I put them on top of that, you will see that the models, both in colors, both in layer resistivities, and also layer boundaries, match perfectly. And this is basically, for me, this validates that this new system with completely new hardware are able to reproduce our old test site data from 2015. My first example is a test survey we've done in central Jutland, and basically we have 25 soundings that are collected in one day by a two-person crew, and we are again using a standard setup and a 10 ampere peak current in the 20. And you see here at the bottom the red circles, they are the stations. And the color is the depth of investigation, and you can see the depth of investigation is between 240 and 260 meters in this segment. The models look like this. It's a very resistive top layer, that's the purple. This is basically a big sandbox. It's very, very sandy down till you get into your blue colors, which are deep lying clay layers. We can also look at the data, and I hope you can see this. It's a little bit, but basically I'm showing the middle panel is the data curve from, and your data starts at 10 microseconds and go up to 10 milliseconds. Data has, we calculate the error bars on the data. They are based on the raw data stack, and then there is done a minimum processing on that. And then it's going into a standard inversion program, and you see the model to the right. It's a smooth model. We see the clay layer in the surface, and then we have the sand layer again, and then we get into this 5-6 meter bottom layer. But just to show that the data looks nice and clean. Then I'm going to take you with an example from Kenya. Yeah, okay. Then I'm going to take you to Kenya, where there has been done some work in collaboration with Water Mission in Kenya. That's an NGO working supplying water for in developing countries. It's Kukama is a township of 60,000 people, but there is a very big refugee camp with around 200,000 people. So we are in the north western part of Kenya, and they actually consider now to make this a permanent setting. Water in this part of the world is very dry. It's a very dry landscape. There's a water shortage in general. There are some very shallow groundwater tables, and you all know, or these who work with water, know that very shallow groundwater tables can be a problem because they get easily polluted. There are also good targets that is known with palachons and fractured sandstones, but there can be fluoride problems, there can also be salinity problems in this area. The boreholes they are making now, they actually make them in the vicinity of the rivers, so they try to find where are the aquifers in the vicinity of the rivers, because that also in the rain season, that's where we got the recharge of those aquifers. So they have done a survey here. You see all the dots is where they have been making measurements with the estimates. And just some pictures from the crew. So this was also a training program, and it took like just a couple of soundings, then the crew were able to operate the instrument by themselves. And at the end, a sounding took 10 minutes and 30 seconds from rolling out, make the measurement, and rolling in again. And then they were off to the next station. And you can see they're working just with a cell phone on the instrument. Just a couple of results. So here I'm showing, this is one of the soundings in the middle of the riverbed, and I'm showing the data to the left, same starting at 10 microseconds, going up to 5-6 milliseconds, so that's basically where we reach the noise level. And we see here on the model to the right, we have some sand layer at the top, then there are an alluvium sediments, probably with the saline water, and then we get into the sandstone bedrock in the depths of around 100 meters. Then there is, again, similar, another example, but where the conductivities are lower, and you get probably salt water in the sediment. So, in summary, I have presented a very versatile sounding tool, can be configured in many different ways, and can be configured for different applications. I think it's cost effective, there's high productivity with the system, and it's very easy to use, just control the app. Also very robust, because we don't have any buttons or anything on the instrument, so there's nothing which can really go wrong. A lot of people have been involved in this, so I need to acknowledge the Geophysics group at Open University, Water Mission in Kenya, Turkana County in Kenya, Innovation from Denmark, and the Coordination Foundation. Thank you very much.
Okay, thank you so much. Yeah, so we'll thank you so much.
Is Dr. Truffert, CEO, IRIS Instruments. Please welcome her with a round of applause. Okay, thank you. IRIS Instrument, but by the way, what I want to talk about is science, okay? And so I will show you an example of 3D electrical resistivity tomography and induced polarization survey that has been done with our equipment, but it has been done by Geophysics, which is a company, an Italian service provider, together with a supplier of water. So the ones who supply almost all Roma underground. So I just want to focus on one thing which is very important today. So everybody is looking for water, okay? We are looking for water even in Europe, even in France, where basically, so 10 years before, we said no, there is no probability of quantity, only a probability of quality. It's wrong, by the way, okay? Today we are looking of water everywhere, and also so in Europe. And you can see that on the top, so this is so just a withdrawal, so just to have a look on where we take more water on the ground. So basically in the US, but also in China and also in India, by the way, so for agriculture, also for the population and for the industry. What is important as well, so it's, yes, for sure, 1/3 of the population so are under water stress, that means so 2.3 million people in 2022, is what I said, and by 2050 it will be worse, okay? So we have to take care about that, we have to find a way, technology speaking, so to find water more and more deeper, and why I say that is because on the right, so you see on the red bars, so this is the average of the depth of the water so in 2017. So you see that it's in any place so in the planet. So we are not the same thing, the same geology, basically. So the geological basin, the sediment, and sometimes with the complex geology, it's very difficult to have a good so drilling with a good rate of recovery of water. And you see that North America, by the way, and also Asia, and also Africa. So the average of the depth of the water table today is rather deep. It's 80 meters. That means that could be 200 meters. Just to have a look, so yes, the fresh water withdrawal, so again, yes, for sure, so Asia is the top, and India, so you definitely need water. I will do that, actually, and there is no way to say that, but 89% of the withdrawal here in India, this is for agriculture, so it's very important. And in Europe, so we are not the same, you see, these are so the recharge, because we talk about so how to deal with taking back water from the ground, but there is a recharge. This is rather good, even for Asia, very good for South America. North America and Europe is roughly the same, but you see that if I just do a closer view so of Europe, you can see that there is difference in the south. In South Italy, so Roma is in the middle, and in the north and the western part of and the eastern part of Europe. So we go to nearby Roma, 40 kilometers far away. So it's a village called Persil. It's really hilly. so it's 600 meters to 1,000 meters of altitude. This is the inner Apennine chain, so, and really it's a bush, okay? So very difficult to do a geophysical survey of it. Yes, okay, thank you. Okay, little bit of geology. So they made a survey at 95 hectares, which is very huge, okay? Because they were looking for water not only for Persil village, but also for Roma, okay? They are looking for nearby Roma in order to bring the water back, because Roma is already a little bit polluted, okay, for the shallow aquifer. So it was really difficult to do that. And so this is, you see this northwest trend. These are the complex, explicative with crust. It's very complex geology, okay? This is, and on top of that you have quaternary sediments. So really a complex, it's not a cylindrical geology. It's not, by the way, it's not easy to do and you need to do. So it's why they did directly went in 3D. And for that, they needed electrical resistivity tomography system and induced polarization. What is it? So it's a sort of resistimeter, but they split, so they separate the receivers and the transmitter because they wanted to go deep, okay? About 500 meters depth, okay? And they wanted to do also in 3D and very tricky land. So what they did, they separate. So they used what we call the full Weber system, designed by Iris Instrument, and this is just recorders, 2-channel recorders. These are the black box on the right, and so it's 2-channel. That means you have two dipoles, okay, just connected with it, and that's it. So the cable is just the cable from the box to the electrodes. That's it. So you do not have to bring so heavy multi-core cable and so on. And then you need also a transmitter because it's an active, okay? You need a transmitter to inject current in the ground and with a motor generator. And basically, when you want to go very deep, you use a high power transmitter, could be so up to whatever kilowatt, but we used to do 12 kilowatt maximum, and it's 25 amps and 6,000 volts, okay? It's not just a small one, okay? And here for this survey, because they didn't want to go so deep, they just wanted to see about 400 meters to 500 meters, so they just use TRP 6 kilowatt. They didn't need more than that. But again, so when you want to go deep, you need power. It's not only the power because it's also the geology and it's also the spreading, so the area you cover. Then you see we are in 3D imaging. And you have these boxes, the small boxes you have with 3 electrodes, so for 2 dipoles. You have no connection between the boxes because they just record with the PPS, the first per second, with the satellite, and it's how we get all the data back. It's very easy to end also in the field. One day to display the alpha day to displace the boxes and to put so the electrodes. You start so the first day in the afternoon, so injecting current. For that you need a transmitter. So this is the box on the right, so the blue box. And you have a cable just to put 1 electrode. If you want to go deep, you need a dipole configuration. That means you need an electrode very far away, and then you just move the other one. If you want to go quicker, you have 2 teams, for example, or 3 teams. And by the way, in 1 day and half, okay, active acquisition, you are finished. But by the way, mobilization, demobilization, and the work, it will take you 3 days, okay, for 1 cubic kilometer of investigation. So which is really good. Another thing which is very interesting with this, as it is so with the resistivimeter, as it is so with the traditional 2D line induced polarization and electrical resistivity tomography, this is we need for water not only to gather get the information of the resistivity, but also the induced polarization, because it will give you an information of the shear. Because you will get the same information regarding the resistivity. You have a high conductivity zone, could be shear, so just with a lot of water inside, could be also limestone. But with also with the induced polarization, that means that means so the features which is the membrane polarization, that means you will have an information of the capacity, the capacitive, facility of underground. So you have the chargeability, you get information about the chargeability of your medium, and basically, so for us here in this example, we're just tracking the shell and some just to decipher shells between and limestone, specifically where we expect it to average. Here the Fourier, so we put 30 Fourier, that means we did up 60, okay, 2 channels, so 60 different diagrams, okay. They realized 44 injection, okay, during the day I talk about. And they let it a long time, this evolution. It's very, very long. They made 35 stack of 2 minutes. Why? Because they wanted to have a very good quality of the induced polarization, but the chargeability on the ground, okay? Because they didn't want to drill within just an alternation of moles and limestone. They wanted to just be within limestone and better fracking that just traditional one. Okay, so 3 days, 15 people, okay? 15 people just spread so all the equipment. And you see in red, these are the injection points. In yellow, these are also the electrode for the receiver. So 3 electrodes by box and 30 boxes in total. And what they did, they wanted to go fast. Okay, they didn't want to just spend time to say, okay, where can I put my Fourier, where can I put my electrodes? So they made that so in the one direction. Okay, the box. And the 3 electrode. One close to the box, another one so just, for example, north pole to the box, and the other one south pole on the box. And how they did that? So just along the track. Okay, they didn't want to go in the bush and to do things difficult, because first of all they wanted to have a block, an image of the chargeability and of the conductivity and resistivity, and they did have it, so down to 425 meters, and you see all the points here, the point cloud of measurement, you do that, and the red dots are the receivers. Here are the receivers, sorry. And then what they did, so they did a 3D inversion, so for that they used a mesh of 12.5 meters. Why they did that? So it's because they did that, so 25 meters, the length of the dipole. They did have a very high resolution, the resistivity, so you see, so the estimated noise for the resistivity was 1% and 5% for the chargeability. Then, you see, just to show you 150 meters, so these are horizontal slices. You still see the northward, so trend, so basically, so the main thrust of the Alpine, structure tectonic, and here, so I will show you, so vertical, okay, I already, nice. These also just to the section to show you where they just selected 3 points where they suspected to drill, and finally, so they decided to drill in the number 3. Because you see that you have a combination of high conductivity and low chargeability, and exactly what they wanted to do. Okay, the point 3 is on the left. But it's on the left. So basically, so they decided to drill here, and you see it's exactly here. Okay, on the resistivity to this section. And they don't have any chargeability, so they suspect they don't have again moles or shells, and so they are drilling now, and they do have good success, by the way. And RCA, so the company, so the water supply company, so they decided to do only 1 well finally, and they just didn't want to do on the number 2 because it was too close to the main thrust. And that means so it could have been very difficult to find the rate of water. And the point 1, so although they have trouble so with the chargeability. So So the conclusion, this DC, so direct current electrical survey, dealing with unconventional, you see geometry, so they put everywhere where they can. It allowed so to cover 95 hectares, so in 3 days. And the survey design was really guided by the environmental constraints. And they did have the resistivity and chargeability, which both help for selecting the drilling position. And the survey highlighted so the mineralogy, the geological variation, techniques as well, and the interpretation, so together with geologists. But yes, for me it's obvious, okay, I was geologist and then I moved to geology, so for me it's obvious that you need also geologists in the team in order to be sure that what you're doing with geophysical data are right. So thank you. Thank you.
Emeritus Professor, IIT Roorkee, as the next speaker. Please give him a round of applause.
Well, good afternoon to everybody. So, before me, Dr. Auken has talked about, say, the TEM, and the second speaker talked about the 3D ERT, basically. I am only looking at what ERI or ERT can do and what it cannot do. Okay? How to complement it by other methods for groundwater investigations. That is how this particular topic has emerged. So I would say that there are some limitations of ERI for groundwater exploration, especially in the hard rock region, and that too in a region where you have got underground utilities and where even GPR can fit. So these are the work carried out in the pandemic years, spanning 2019 to 21-22. And in fact, some of the authors whom I have mentioned there, they are my former students. In a 3 years work continuously we worked on the campus. And the campus is IIT Bhubaneswar campus. It's very much in the peninsula, coastal part of India. And where you have got the hard rock basically, and groundwater exploration is going to be challenged. So anyway, the talk is as per the titles mentioned here. This is the overall thing. And what I wanted to do is, first of all, I want to concentrate on gaps in knowledge and how we can address these gaps in knowledge, and that can give us a handle for groundwater exploration in hard rock. Well, this is the study area. It falls within the almost metamorphic region of eastern mobile band, and where we have got hard crystalline rocks like granite and chondrite, which have a low porosity and permeability, absolutely. For permeability, where the fractures are there, good. Otherwise, it's going to be a tough challenge. And we need a complex exploration strategy. And here I would recall the famous work done by our Professor Shakeel Ahmed. And I remember that he has done it for the hard rock region of Karnataka. Okay? So that was also one point which has triggered this particular research. So the groundwater exploration in the hard rock region is going to be a challenging task. That too in case of subsurface utilities, this is much more challenge. Okay? And of course, when once you can do it by a combination of methods like microgravity and ERT, one can make use of the microgravity to estimate the groundwater storages. Well, this is the study region, and in fact, the study region is shown here. This one. Some difficulty is there. Well, this is the region. This is a small region in that complex surroundings. And in fact, we have made use of the microgravity here for the simple reason that we have got the world gravity map, and we have investigated that first. And this is what has been gathered from the say Orissa Space Application Center, this particular map. And what you can really see is with the horizontal lines which you can see are the inward fracture systems based on the gravity. Okay? And 4 such profiles are taken, A, B, C, D, E. Unfortunately, the resolution is a bit poor, and we'll come back to that, address it in a proper manner in the upcoming slides. This is only to show you the geological background. I will not dwell too much on it because time limit is there. So the gaps in knowledge means electrical resistivity imaging tomography fails in regions with underground utilities. In fact, it is my campus we have to carry out the survey, and with a lot many underground utilities were there. We burned our fingers trying out ERT and ERI because absolutely it was failed, even including GPI. Okay? So ERI and ERT are based on the Poisson's equation. It cannot have depth-wise resolution for coincident fractures. And serving as groundwater aquifers even under ideal no underground utility states. This need to be mentioned or to be stressed so that I will address it subsequently. If you look at the microgravity, you can detect the groundwater bearing fractures but lacks depth-wise resolution. So how we can combat it? Well, if you have a drilled well, at least one well at least, so we can use it as a constraint to reconstruct the aquifer geometry using the gravity. So what is the novelty of this work? We have carried out the usual microgravity data acquisition is carried out almost 6 such profiles within and around the IIT Roorkee campus. So these are the students who have carried out this work for me, in fact for them, their own dissertations, to have a combined methodology for groundwater sake. Coincident ERI and microgravity profiles were carried out at the periphery and vicinity of IIT Roorkee campus, and the interpretation is aided by one more drilled well, and that too the credit goes to CGWB. Okay, only one well is there, and that we have used as a constraint. So beyond that, it is a gravity by stripping that helped us reconstruct the signals, total signal that is observed, and how we can decompose that signal into multiple aquifer signals. Okay. Well, and I think Dr. Chandra was mentioning in the initial forum session, he said something that ultimately you have to drill it and find it out. That is right or wrong. Lucky enough, based on our prediction, a drilled well was there and it did give, it is a successful well. So the methodology involved 3 coincident ERI and microgravity profiles in the periphery or in the vicinity of IIT Roorkee campus. Within the campus, we have carried out 6 microgravity profiles, and microgravity data as per norms have been processed, and gravity by stripping concept is used for mapping 3 groundwater aquifers, and one verification validation is outside the campus, of course, that will give you results. Well, this is a textbook material. I'll simply skip it because you can use the microgravity to compute how much amount of groundwater is held by the fractures. Okay, this is a normal thing, excess mass estimation, and convert it into true mass. This you can find in standard textbooks. Well, this is the study area. As I already told you, the campus is located, seen in this white colored boundary, and the number of profiles that we have carried out are A, B, C, C dash, D, D dash, E, F, and G H profiles. And on the periphery, we have got MN profile. It is a continuous profile carried out by one of the initial work done by Moria or Dhaglaram. And 5 meters spacing is considered there. And within the campus also, the AB profile was having a 5 meter station spacing, gravity spacing. Please keep in mind, it doesn't mean that we have not carried out ERT. Yes, we did carry out ERT, but within the campus we have failed. And on the periphery, like MN profile, this is outside the campus, ERI is good, but unfortunately the combined signal is giving problem to identify the individual signatures coming from the different aquifers. So I go to the next one. This is the one well created, by CGWB on the campus, and this is the lithography, and you can see clearly there are at least 3 such depth-wise aquifers held by the fracture systems, of course, and these are going to be our constraints for gravity inversion. And this is the one I am talking about on the periphery of the campus. And ERT was successful in locating, at least one of them is successful in locating the fracture held aquifer. For the gravity, we have inferred another such region, but unfortunately that is not covered by ERT. So that is still a gap there. Otherwise, the low gravity signal you are getting and the ERT are coinciding. And this is only to tell you as to how you can separate out the regional from the residual at the periphery of the IIT campus where microgravity have been acquired. Normally, whenever you see such a graph, immediately conclude it is a fault region. No, generally it's not a fault. It is in fact the low gravity created by the fracture occupied by groundwater. That also creates a low gravity signal. Okay? So this gravity that what we are seeing here is the regional residual separation, and based on that we are able to dismember that into 3 signals coming from 3 aquifers. Well, this is a constraint gravity model for the 3 aquifers. I told you already we have taken the constraint from the well, and based on that individual responses are shown here. And this is the geometry gathered from microgravity for that particular profile which is on the outside periphery of the campus. Now, the next one. These are the ones I am talking about. The same profile which you have seen, the OG, that is the profile. And in fact, OP and MG, these are the two ERT profiles which you have seen earlier. But for gravity, it is a continuous one. AB and CD, I think that was a nomenclature is given by Dhaglaram, my first student, where the ERT has been carried out, but it was unsuccessful. Okay, only on the periphery we are successful. Okay, so some of the details are given here. I can skip it because time is one thing I think that doesn't wait for any one of us. Okay, now I will go for a within the campus microgravity. Okay, where ERT has already failed. And then based on this microgravity signal, regional residual separation has been done as per norms, and then we have gone in for the modeling, the constrained modeling, and here are those details here, the shallow aquifer, the middle aquifer, and the bottom aquifer geometry is clearly shown here. Then we go for outside the campus, and in fact, the gentleman who will keep his hands there on, he is also a professor there, he has got a small site. He requested me, why don't, because I have already failed in locating the groundwater, I have already spent so much of money and it is his own property. So I told, okay, he is after a colleague of mine. So we did go there and carried out the survey with the development methodology, that is the site which is placed in place. Okay? And both ERT as well as gravity were taken into consideration. And this is the ERT, wonderful. You can see here, as though on the right side, the blue one, low resistivity, goes all the way from almost 18 meters to 87.9 meters, a continuous zone. absolutely, as though it is a continuous fracture holding the groundwater. Gentlemen, it is not so. It is not so. Okay? It has got 3 separate aquifers, and the signal is because of the fact that it is a controlling equation, the Poisson's equation. It cannot have the vertical resolution, no matter how we try, extend our ERT, can do this, can do that, but you should not forget about the theoretical limitations of the method. Okay? And now, taking the gravity, microgravity into consideration, we are able to same one drilled well, which is within the campus, away from this place. Okay? We are able to get the individual signatures of the aquifer based on microgravity carried out on the same profile.
Please conclude.
Well, these are the aquifers which were depicted on the basis of microgravity, and drilling has taken place on the same profile, the same location. Next slide.
टाइम ऑफ होने बंद हो गया टाइम ऑफ हो गया ना बंद हो गया
Take more time.
This is the one which we have. The drilling has taken place, and it has given rise to copious amount of water from all the 3 aquifers which were predicted. Please keep in mind, they were predicted on the basis of combined methods, both the microgravity and ERT. Well, I already partly covered in the discussion. ERI cannot have depth-wise resolution, fundamentally owing to the governing equation, and the basic inversion procedure based on the locate Marcus algorithm transforms hollow pseudo-section to true resistive systems by utilizing the depth of investigation sensitivity function concepts. Sensitivity function for Bernard-Schubert consideration well suited for depth-wise investigations. Underground utilities hamper ERI and GPR investigations also. So within the IIT Roorkee campus, they failed thoroughly in groundwater investigations, but only microgravity has succeeded both within and outside the campus, but needed the support of lone drilled well within the campus. So gravity by stripping has come to our rescue. These are the conclusions. Microgravity based groundwater prospecting, a hot rock TCM with underground utilities is an alternative where conventional ERI, ERT and GPR fails. But doesn't mean that one should go. You should take the help of ERT to locate those, to confirm those zones. The subsurface groundwater bearing fracture zones can be delineated by microgravity anomalies aided by at least one drilled well, because that also suffers from ambiguity. That's the reason why we need one drilled well. The amount of groundwater of all fractures calculated through the true mass estimation formula by Parasis came to about 10.2 gigaliters. Okay? During the time when the data acquisition has been made, I cannot say for time immemorial, during that period, okay? And this work has been carried out by 3 students in 3 successive pandemic years, where we cannot venture outside the campus because they were, it very well.
They did gravity.
Thank you, sir. Thank you so much.
These are the acknowledgements.
Very useful. You can read that.
So, I convey my sincere thanks to the director, head of the school, for extending the facilities in successful completion of the presentation. Thank you, sir.
Thank you so much.
Thank you.
Please, all the speakers that
Titled CGWB. Please welcome with a round of applause.
You can say what is the role of tomography in delineation of cavities and sinkholes. Our study is pertaining to the Bundelkhand region of Madhya Pradesh, which is occupied by genetic terrain. In between there are some limestone patches. And the area is infested by various cavities and sinkholes. This deep pool is a very famous tourist place in the area. Many people have tried to go inside in this cone, but nobody can estimate the depth of this cone. And everybody says that the water is very much flowing in that cone. And this is the second one is the Arjun Kund. In that, if you enter in that kund, you will go 200-300 meters. You will see a just kind of lake or you can ocean where your eyes will go. It will look like say water and water. And this is the Patal Ganga. This is the very small hole on the top, about 5 meters. If you enter in that cavity and you can move up to a kilometer, and again you will see the huge water and water. And lot of things I am not going in detail because time is so. We did some tomography. About 14 tomography in that whole area. These are the signatures of the tomography and these are the location where it is not exposed on the ground, but we have drilled the borehole and found the cavities also. So this is the utility of tomography, which can eliminate the this cavities and sinkholes. So these are some results of the investigations. The most important results is the last one: 3 boreholes still surrounding the beam kund yielded enormous water in the limestone rock. The several studies done in the area indicate that depth of beam kund is more than 80 meters. Because of flow of flowing groundwater, depth of kund could not be measured. Depth of water level is about 30 meters in the kund. So now the questions comes: if the water is flowing in that kund, where it is going? This question was asked in Hyderabad once I was presenting that my paper. At that time I was confused, and that same gentleman says that either it may go into the ocean or it may go into the river. But ocean is very far, about 1500 kilometers from that place, and this water of this kund are so deep, about more than 30 meters, and surface of river is about 5 to 10 meters only. So it was very problem to me to explain the things. But after some times I was seeing the Google image and I see that there is a lineament. You see this is the Bhim Kund, this is the Pandav Cave, this is the Gupta Godavari, and this is the Triveni Sangam of Allahabad. So I everywhere, like Bhim Kund also, in this Pandav Cave also, if you go and see, there is a deep water. Whole year you will get the water coming, but nobody can see where it is going. Even in this Gupta Godavari, everybody knows in Chitrakoot there is Gupta Godavari. It is also very deep water, and but water is coming, but where it is going, it was not clear. So I studied this lineament and found that geologically this lineament is infested with limestone rock. Pijawar in southwestern part and Vindhyan in northeastern part. It is seen that the large number of water pools and cavities caverns exist along this giant lineament. Some of the famous pools of water like Bhimkund, Arjunkund, Pandav caves, like so many things are there. Gupt Godavari water is also there, as I told. So the question, I was normal some observation of mine that you might have heard that earlier when no deep drilling was there in Bundelkhand region, there was huge migration of the people from the. So I can say that this lineament is providing the conduit to the groundwater, so the water flowing very speedily, and aquifer is top aquifer is desaturating very fast. And you see there is a cave river passing to this lineament. We studied that the water of this near Panna is EFX. At Bada it is going minus. As per river hydrology, this water should increase, instead of it is decreasing. Means some of the water of this Ken river is going to this lineament. It is also found that some of the borehole drilled in the in this Bada in Bada district in such formations have built huge water discharge where drilling is not possible beyond that. The boreholes drilling data Prague reveals that the basement rock are near the confluence of Vindhyan limestone, shale and sandstone. The elevation of Bhimkund is, this elevation is about 430 meter and this is the 100 meter. So the study showed that there is a possibility of subterranean flow through the interconnected network of sinkholes and cavities in the carbon rock formation, which constitute southwest to northwest trending linear body. The hidden subterranean flow meeting at the Ganga-Yamuna confluence at Prayag may be the invisible Sastry river of Hindu legends, which are unrelated to the Vedic Saraswati rivers of Western India. My saying is that the Saraswati river, which originated from this Himalayan and go to the Arabian Sea, is nothing related with this my study. Such long subterranean interconnected passages are not uncommon in carbonate rock formation. Example of these are the 6 kilometer long Mammoth Flint Ridge cave system of Canterbury, USA, the 34 kilometer long Kiran latent earth of Meghalaya, and the 3.5 Belam caves of Andhra Pradesh, which is still being explored. Thus, the probability of the presence of nearby 300 kilometer long subterranean passage of water flow can be expected in this area as well. So, I conclude that linking this observation with research work of many scholars and myths already prevailing about the invisible river at Prayag, the study postulates that the unseen river Saraswati at Prayag is a groundwater flow which originates from Bundelkhand region of Madhya Pradesh, follow the extensive deep lineament cavities, caverns, and convert to the confluence of river Yamuna and Ganga at Prayag, that is Allahabad. It is evocative that the nature and extent of these cavities, caverns may further be discovered by application of by application and integration of various latest geoscientific techniques. Also, the study further suggests that the existing large prominent cavities may be developed as a geotourism. So this is the conclusion, and the submission is that my study is not related to this Saraswati, because so many times people confused with this, why you talking about the Saraswati name like that. My study is only that is related to the existence of Saraswati at Prayag, because nobody, our ancestors teach us that Ganga Yamuna Saraswati is Allahabad, but no scientific evidences says, no scientist formally says that there is an existence of Saraswati. But I feel that at the time when the desert era was prevailing and there was no rain and no water in the Ganga and Yamuna, people might have seen that this water is emerging from at that place. So that's why they have thought that the Saraswati river, which has lost in Gujarat, Haryana and all these things, had emerged here. That's why they might have felt that this is the Saraswati river. But my study says that no, it is not like that, because in Haryana, between Haryana and Prayag there is a Ravli, so there is no possibilities of coming to Saraswati at Prayag. But my study says that this will be the Sastry river in the form of subterranean river, taking the groundwater from the Bundelkhand region, emerging at the Kerala. Yeah, thank you.
Okay, thank you so much.
Good afternoon. So I am going to present on actually the testing of the vertical resolution of airborne investigation from near surface mapping. This is done by the Kotala Bhimraj, who is the PhD scholar at Academy of CSIR, Scientific Innovative Research at NGRI. So as we can see, that there are increasing application of airborne electromagnetic surveys globally as well as in India. Like almost 2/3 part of the Australia is already covered by airborne EM, and significant portion of Denmark, Australia, America, whatever the developed countries we can talk, and most of the countries they have applied this technology. And in India also has been covered quite good portion for mineral, for geological mapping, and in the 2013 we have started for groundwater applications. So there has been a lot of discussion as what the system we must use for the groundwater, because groundwater necessitates to have a knowledge of the deep aquifer, including from the top surface. So we can say, but soil to the deep aquifer with the groundwater pathways, how the recharge process takes place and where are the deep aquifer setting. Because mineral can be deposited once and we can exploit it, but then water is getting replenished every year. So certainly we need to have knowledge from topsoil to the deep aquifer. And we use in that process number of skeleton systems, like starting from 304 to 306, and now we are using 30312, which has 500,000 NIA for high movement and roughly 3,000 for low movement. So but then what is the actual resolution, vertical resolution at the field scale? So just to again say that, like being, as the name is dual moment, we have a small pulses where we try to see the very shallow level, but then alternatively we see the large pulses which has which is actually the high moment. So these alternate pulses of low moment and high moment, they are transmitted and we record the signal during the off time. And if we look into detail, this is the main layer actually that induces the electromagnetic field as an impulse response, which we try to record during the off time. So this is the recording, and if you see here the RAM, I mean it starts actually from here, and by the time it becomes completely zero, roughly it covers almost 300 microseconds, and actually the electromagnetic the signal start receiving from here itself. So the shallow information, I mean the time we can say that time can be converted to depth. So early the time, shallow the information, later the time, deeper the information. So by the time 300 microsecond comes and we get actual off time, we lose the shallow information. So where this low moment, if you take the same RAM, the RAM time is 10 microsecond. So that means we try to fill the information in between from 10 microsecond to 300 microsecond. So low moment response you can see here. And so that means lowering. And if you see the approximate depth calculation given by Mezu 1995, for 10 millimeter density it comes around 4 to 7, I mean roughly 5 meter depth, or you can say 4 meter depth. And if maybe 50 meter, you may get 6 meter. So earliest or shallowest information you get roughly from 5 meter depth downward. But and if you take the case of hard rock, the thickness of the soil limited within 3 meter, 0.5 to 3 meter, sometimes absent. So certainly the recharge processes are controlled by the soil, which is completely missed here. In order to further complement the Auken, the Esben is sitting here, they have further given another approach and tried to see that how further we can improve the cellular resolution. So in fact, during this period, when RAM down is completely not zero, the current pulse is completely not zero, there is a primary field as well as there is secondary field, because the secondary response start from the pulse starting from here itself. So there is a primary as well as secondary, and it has been described that what we measure the voltage in the receiver, where NA dB is stepped by dt, and this system response where di by dt is nothing but a time derivative of the current transmitted in the transmitter loop. And here all electronics and the reflector, whatever you use, so this you can say the primary is called from the transmitter as well as electronics involved. So this is the way we can further come out, and at the test field side what they have come out. So this is a 10 microsecond line, and this has been further advanced to from 3 microsecond to 4 microsecond. So that means the time advancement is nothing but the depth advancement. So like then you further get shallower information. This item, the company, they have come up with a proprietary technology, and the more the elevation you increase of the transmitter, your signal level drop down at certain. So if you keep increasing the altitude, your signals keep dropping down, and for low moment at one point of time, it becomes almost zero, no response from the ground. And at that height, we take out, cut the data. Actually, whatever the decay curve is given there, that is actually the contribution from the system or the primary response. So those records are taken. So for example, you can see here, this is a total response, and out of this a primary response, and once you subtract from here, you get this noise at the high altitude level. So this is totally noise, and once you bring down those the loop, close to the ground, you get the response. Of course, the system response always remains there, primary response, but then ground response also coming together. And once you subtract this, then you get this decay. So that's how we get the actual ground response during on time. So and this is the field response from the Surat area, what we have actually measured from India, where we could see the usable grade from 4 microsecond onward, and if you approximate the depth, it starts roughly from 2.5 meter to 4 meter. And this is the area, at the Bay of, Arabian Sea, close to the sea at Surat, in the Gujarat state. And now, since we are talking mostly on the low moment, so we are confining to the alluvial cover. And actually, this study has been carried out in the peri-urban areas of the Surat, and a lot of light line you can see here. And if once we have inverted the data along this light line, this is the response. Unfortunately, the resolution is very poor. It's not the actual. We have got the result. But you can see this is crossing the river. So this is along the river. So actually, this is a river channel deposit which comes with a high resolutivity. This is the scale. And if you include the system response, the R-type modeling data, the resolutivity got improved. So actually, what we are talking about the resolution only, sir. This is the data, the 10 microsecond. Actually, the modern data is always taken from the shallow level, but the actual resolution is not from very shallow level. It is mostly interpolated. But then if you see, once you start getting more the sensitivity because of better resolution, we get improved resolutivity over here. And so actually this was with the 10 microsecond, is from 4 microsecond. If you see together the response, this is the change in the resolutivity, order of resolutivity, and it is because of the shallow resolution. And so that was about the modeling of the same airborne system with 10 microsecond, starting from 10 microsecond and starting from 4 microsecond with on-time modeling data. And this is again we are comparing with the electrical resistive tomography. And at this depth, at this point, if you see, at vertically, this ERT was acquired at 10 meter electrode spacing, and the results are quite comparable from shallow. And certainly the 10 being more sensitive to the conductivity, so the conductivity is given a bit more, and whereas the ERT gives more, slightly higher order of resolutivity than the 10. So these are the intrinsic property of the methodology, but then they are following almost the same trend, and we can say that they are comparably close. And this is the comparison with the borehole data, and we can see this the real result and both how they are responding. And actually this was done for the French well in the Surat, where engineers have used this information for conceptual radial well in the in the river, and they have given the sediment with the particle size of different like gravel, coarse sand, fine sand, medium sand, and you can see the resolutivity in black color, and this is the gravel and coarse sand, this is a percentage, so you can see they are following very well, and then opposite to the K and the silt percentage of the sediment. So these are the two wells, but then we have done around 10 wells in this area. So what we can see that this is of course the ongoing process, and now once the system we use with the on-time modeling, we could got the from 4 microsecond onward the resolution that gives around 2.5 to 3 meter from downward. And thanks a lot. This project was sponsored by Surat Municipal Corporation, and of course the team of NGRI has been working on this. So thanks a lot for the opportunity.
Thank you so much.
There lies the contribution of CGWB. Basically, we have got lone drilled well on the campus, and geology is not changing so fast. So that is a boon for us. And practically using a single well, we could dismember the gravity signal into 3 signals simultaneously and reconstruct the geometry of the aquifers. And that has been proved by drilling, because I told you, one of my colleagues, of course, he is much younger to me, and he had got a small problem. He said, I have wasted my money. It's a hard-earned money, 3 lakhs of rupees I spent. And coming to the point that with single ERT on the same profile, microgravity, with 10 meters spacing, it has been done, and the signals were there. Low microgravity and low resistivity signal coming with the ERT. But ERT could not resolve the individual 3 aquifers.
But microgravity can also...
Yes, I agree fully with you. That's the reason why we have taken the help of one drilled well inside the campus to take into consideration the gravity by stripping. Okay? That concept we have used, and then we are able to succeed. Anything more, Dr. Chandra?
Thank you.
Thank you.
Dr. Subash, probably you may have to take help of Dr. Professor Sastry for carrying out microgravity survey in that area and find out the and then it will try for Musalamasi.
I am searching such agencies who can spend some money to investigate the area of that same linear, subterranean flow. So that is necessary, because only just seeing the lineament, these things cannot be confirmed. But for that, we need some money, and I am searching collaboration with.
Dr. Subash, you have not told anything about how you can improve the near surface resolution.
Presentation is done generally.
You have not strictly told how you have improved the resolution. Just please tell me 1 or 2 sentences.
Actually, the time is the depth. And what we can say that, the impulse contains infinite sum of the frequencies. Higher the frequencies, cellular informations. So the most early you get the cellular information. What we are trying to say, like there are a number of systems, they start measuring, the RAM. So more the sharper, better the larger range of the content of the frequency, and the more the early you start measurement, I start measuring in the receiver and utilizing, you get the cellular resolution. So what we have tried to say that just to compensate, there are 2 moments, and out of 2 moments, low and high, we have also used on-time modeling to further improve upon and get the information from 4 microseconds onward.
Okay, right. So let's move forward. Question from audience side.
Sir, I want to make one point on ERT.
Please use the mic.
Sir, I have one. The RMS error is around 27%. Generally, we only have around 4 to 5% RMS error, and if it is more than that, then we have the doubt on the data. Another thing that when you have such very small variations, then what we have seen that Schlumberger as well as Banner, they do not give good results. So dipole is always giving you the best results. So I think we must see the profile also with dipole and with the RMS error not more than 5 to 10%. This is my just observation.
Thank you so much. I think this is the question.
Can I answer?
Very good. Because we are getting late.
Dr. Kapil, very happy that you have pointed out issue with the RMS error. That is apart. Please keep in mind the entire success of ERT is based on Loki and Barker's algorithm. Do you agree or not? And that has inherently there is a deficiency, because as the depth increases, the size of the cells keep on increasing. Okay? And thereby it lacks resolution. So in this particular methodology, which with the help of my students got developed, is basically taking the strengths of two methods. One, microgravity, and that of ERT. And always keep in mind the ambiguity. Ambiguity exists for both of the things. But with microgravity, one rule is that you have the gravity by stripping. Sigmund Hammer, way back in the 50s, he has proposed that. Okay? So, as per that, you can additive nature of the signals we have exploited.
Thank you so much. Any more questions? Please raise your hand, otherwise we close this session, we conclude over here. Right, so I think this is have been an important, because water resources, of course, is an important part of the geophysical.
These are authors with the token of appreciation.
That's for Dr. Captain, it can't be exchanged. Sir, that's for Dr. Captain, it can't be exchanged.
Golden for men and silver for ladies. Yeah, I know. But what to do? My vendor thought that it's the other way around.
I would please like to call Dr. Tiutia on the stage for facilitating our chairperson for the session.
Pleasure.
All the authors are...
Sir, please.